what you need to realize is that middleware sits between applications and the operating system, right? And I've told you that the main purpose of middleware is to hide everything that has to do with distribution. Now, the question then pops up is what do you put into middleware? And the answer to that question is actually a very simple one. Everything that is common to all applications. So to give you an example, fault tolerance is something that every distributed application needs. Well, if there's a kind of a general solution to handle fault tolerance, that means that you put that solution into the middleware. Okay? I'll give you another example. I talked about coupling all kinds of legacy systems by means of communication. Well, you can have very application-specific solutions for that, but hey, this is a problem general to distributed applications. So you come up with a solution that you then put into middleware, or actually, this is the way how middleware is formed. Are you all with me? So here you have it. Middleware contains general-purpose solutions that are good for everyone. Everyone, in this case, are distributed applications. Then you will instantly bump into a next problem saying, well, the general solution that has been put into middleware may be good for lots of applications, but it's not good enough for mine. And you always see this. You even see this with operating systems. If you want to have a specific application running on an operating system, there will come a point in time where you think that you should tweak the operating system. And this is often done by means of configuration. Now, we really do understand operating systems, and I would claim that we understand to a much lesser extent what you do or do not need in distributed systems, middleware. Okay? So that's the problem. And this leads to the observation that what you really need to do is to be able, work for me. It's not working for me. I'm not sure why it's not working for me. Okay, I just think I just lost this thing. Okay, tough luck. Here. This is the key issue. Adaptive behavior of middleware is what you need when you actually provide a middleware solution. And there are many ways of doing this, and one of the simplest ones is by means of an interceptor. And this thing is actually really having problems. An interceptor is, as its name would suggest, a mechanism that allows you to gain control over when things happen when you actually call a service somewhere. And the model to think here is the following. One of you said that when you think in terms of middleware, it's actually a piece of software running on a specific machine. Well, that's the way how you implement this, of course, okay? And I said, well, all these pieces of software running on these different machines, they collaborate in giving you this idea of a distributed system. But what's important here is that you will see, okay, I think this thing is almost failing on me. What you will see is that there, I'm trying to get this mouse to move. If I stand, closer to this, yeah. If you take a look at this piece of software, that's your middleware that resides on your machine. If you want to make this concrete, Apache is a piece of middleware. Okay, you just install this as a bunch of processes on your machine. On top of middleware, you run applications, and the middleware sits on top of an operating system. And let's just have this model that you have a piece of client application over here that wants to have something done at an object or a server on a different machine. Okay? So what you would normally do is the following. You would be offered an interface at the client application to call this do something with a value. And then the normal flow of control would be that you call this thing, you go through the middleware hands it over to the operating system, and it's out there in the network. Okay? Now, once you have that, And you know, the middleware can do stuff, and the operating system can do stuff. For example, what the operating system will do in the end is translate that call into ordinary socket calls, send-receive statements. Okay? And what the middleware perhaps will do is it gets this call, and it will transform that call into messages, a series of bytes, that are then put as payload into the send and receive statement sent by the operating system. Is this abracadabra to you guys, or am I still making sense? Okay. Now, what you can do, if you want to change the behavior, is insert interceptors. And here's one. Here's a request level interceptor. And what this thing does is say, okay, I won't tell the application, but when it says b dot do something, I will pick up, I will pick up this message and I will modify it. Okay? And then as soon as I've modified it, I will hand it over to the middleware. And in turn, the middleware could say, good, I will pick up this message before actually handing it off to the operating system. Now, the key observation here is that you insert the interceptors. They're yours. Okay? So there will be hooks in the middleware that will allow you to insert a request level interceptor or in this case, a message level interceptor. And what could these interceptors do? Well, to give you a very simple example, and the one that I give actually every year, suppose that you have a replicated server. Now, a client should know that a server is replicated, okay? But the consequence of the replicated server is that when you call it, your request should be forwarded to, let's say, 3 of these servers. But the client shouldn't know. So what you can do is you can insert a request level interceptor so that the client will think that it's calling a single server, or if I'm precise, a single service, and the latter one is correct. That request will be picked up, and the only thing that the request level interceptor does says, but I know that there's not just B, there's B1, B2, B3. So what I'll do is, I'll copy that request, and I'll send 3 requests to the middleware. So basically, replication has been handled by means of a request level interceptor. If you have 5 servers, you insert your request level interceptor, and it modifies that flow of control in that way, without touching the core middleware. Yes?
Well, the client has to know the first entry point.
Yes?
Every client will go to the same one, otherwise then it becomes like centralized.
No. The only thing the client application has is a programming interface. It's a library. And in that library, I'll come later on to the actual implementation of these things, and the library says, hi, I'm an object, call me. In this case, it's a so-called stub. It's really a proxy. It behaves on behalf of the service and is implemented on the client side. Okay? So the only thing the application does is b dot do something. Got it? And then? And then what happens in that library, there's a hook for a request level interceptor. And it says, well, you know, if you call this thing, you redirect that call to your request level interceptor. And what happens is, hey, I'm going to call B1, B2, B3. For those of you familiar with object-oriented programming, it's basically a form of polymorphism, where you just take the control and you simply modify the code. This is everything on this picture is on the client side. Okay? It leaves the client when it leaves the operating system. Okay? Now, yes.
Based on the example you did before, would be an interceptor module of Apache. So these modules that Apache can activate.
I'm inclined to say yes. So for those who are familiar with Apache, is a request level interceptor comparable to a module in Apache? I'm inclined to say yes, but it's not a one-to-one mapping. I'll be explaining Apache later on when I discuss web-based systems, which is far down the road actually. But for now, yes, you can think along those lines. Now, a typical example of a message level interceptor could be when you are going to transfer a really big file. Okay? Let's just exaggerate things a bit. A 1 gigabyte file. Okay, so the client now has a 1 gigabyte file and needs to store this on this replicated server out there. Now, sending 1 gigabyte of data directly over the internet is not such a good idea. What the operating system will generally do is chop up this 1 gigabyte file into smaller messages. Okay? But it may happen that you know the best way to chop up this file. So here's where a message level interceptor comes into play, because at the point where the middleware is planning to hand over the data to the local operating system, you could say, well, middleware, before you do that, hand it over to me, and I will chop up my file because I happen to know that this is a file that needs to travel the entire internet, so I'm going to chop it up into 512 bytes because I know that is guaranteed the minimal segment size that will go through the internet without being chopped up any further. Okay, that's a guarantee that the internet gives you. If the operating system had decided, I'm going to chop this thing up, let's say in chunks of 2,000 bytes or 2 kilobytes, then you may have the risk that it will need to be chopped up later on as well. The network will handle that, but maybe you just know that, hey, I'd better chop it up in 512 bytes anyway, because I know that's going to be the most efficient for my application. And again, you can assert a message level interceptor to intervene in how the middleware actually would handle its stuff. Okay? Is this clear? You got to know the difference between the two. Okay? Every so many exams I ask something about how you can change the middleware. Yes?
You said that the request level interceptor, you put it there for the application or something, but the message level, who puts there?
You.
Also?
Yeah. So you have to realize, and whether you're an application developer or the middleware expert or you're teaming up with the application developer, that is of less concern. The most important thing is that you leave the middleware itself, the core middleware, untouched, and you are offered these points in the middleware where you can actually intervene. And you can modify the default behavior of the middleware. Okay? That's the basic idea. Yes?
It will work for all the client calls happening, or is there a way where...
Good question. So would this happen for all applications? No, you can do this on a per application basis. Okay, so the interceptors can be tied to a specific client application. My mouse just left me again. I think there's something here with the transmission. But okay? Yeah.
But then the system must also be aware that interceptors might be used, because if you use interceptor to chop it up into small pieces and then give it to system, and system decides that pieces are too small, then might latch something.
So absolutely. You don't necessarily. So basically, I'll repeat your question. I would rephrase your question like, hey, do you have full control? No, you don't. Okay? Because the operating system, if it's a really intelligent operating system, it may decide, well, you can give me 512 bytes. I'm not going to do this because I know it just happens to be TCP. I'll just stack all these things into one buffer, and then I'll do the chopping up. Okay, so that's where you go. Okay? So you're not full in control, but you can at least, at the very best, give some hints on how this thing should be doing it. And maybe the operating system will not be so intelligent. Yes?
You said a good example to request level interceptor was
Replication.
to the server.
What? If I would have a replicated server, so I have a service, let's say I have a storage service, but I would like to have my data replicated for fault tolerance. So how would I implement that? By means of, for example, 3 servers doing exactly the same thing. The client application should know about the fact that these servers are replicated, but what it should know is that, hey, if I just invoke this storage service, then my data will be stored 3 times. Got it? Yes?
What happens when one of the servers doesn't?
Don't worry, there's a whole chapter on fault tolerance. Okay? I'm not talking about that right now. I'm talking about a mechanism as an illustration of a mechanism where this mechanism is useful. Indeed, for modifying the middleware in the case of replication. Okay? Yes?
In case of message level interceptors, when I send it as an object to do some function, I define an object as a data and its corresponding function message.
Mm-hmm.
And what do if I break the message as into smaller chunks, I give incomplete information to an object.
Ah, okay. What do you think is there on the recipient side?
It's a function which is working on and off.
No, hold it. What do you think if I would chop up my messages to the storage server, but the storage server doesn't expect chopped up messages? What do you think will be on the server side? What about a message level interceptor? Okay, but I like the question because I'm suggesting that the flow is only from the client application to the operating system. Okay, but of course it's also the other way around in this example, also on the server side. Okay? Okay, let's move on. If this thing will work for me. Oh, what is this? Sorry about this. Okay, let's talk a bit about adaptive middleware. And I may decide to stand here a bit because then at least I will get the movements on the slide correct. When people talk about adaptive middleware, they say, okay, are there all kinds of other techniques that we can apply that will give us the flexibility that we need? And there are basically 3 techniques that people have been applying. It's called a separation of concerns, computational reflection, and component-based design. Okay, now let's start with the first one. Separation of concerns. What you try to do is to separate core functionality from what is known as extra functionality. And let me give you an example. Back in the old days, 10 years ago, 20 years ago, there was this big debate on parallelizing compilers. It's actually still a debate. Actually, there are parallelizing compilers. And the big idea there is that many applications operate on big arrays. Okay? Basically, it's all matrix multiplication. And if you happen to know how the data is actually stored in an array, let's say that you only have data on the diagonal of a, oops, I should do this like this for you guys, on the diagonal of a matrix. Or that you happen to know that conceptually it's a very big matrix, but hey, in fact, it's only a sparse matrix. Only a few elements actually have data. Well, what you would like to do is to write, let's say, a Fortran program that doesn't deal with these things. You know, it's just a matrix and it does its multiplication. And what you would ideally would like to do is to tell the compiler, hey compiler, this is not an ordinary matrix, this is a sparse matrix. Or this is a really sparse regular matrix, and let me tell you where the data elements actually are. Okay, so the other part, what I'm just mentioning, that's extra functionality. If you provide the compiler with that information, it can optimize its compilation process and actually generate code that is optimal for sparse matrix operations. That's called a separation of concerns. Okay, so the whole idea with a separation of concerns is that you separate the extra functionality and later you weave them together. Now the example that I gave is actually a good one because that's where it has been done in reality. In many other cases, you basically see, to my view, toy examples. Progress is being made, by the way, so I shouldn't be too blunt over here. Okay. There's another one that's called computational reflection. This has something to do with how many of the computer science folks actually deal with problems. If someone comes to you and says, okay, I have a problem, then we are training you to answer this problem as follows. Listen, I can't solve the problem, but I can build a really good tool that can help you solve the problem. It's called a level of indirection. And computational reflection kind of fits into that corner. What it does is, listen, I'm a program, I don't know what's going on, but I can inspect myself during runtime, and where needed, I can change myself. Okay? So a program inspects itself, adapts or changes as needed on the fly. What you see is that you apply these type of techniques typically at the programming language level. I'm making the claim here that its applicability is somewhat unclear, which is not a black and white statement, but there are too many examples where you would see, hey, was this really needed? To give you an example that we actually already discussed, the separation of policies from mechanisms kind of fits into this scheme. Okay? A very strict separation between policy and mechanisms is actually kind of computational reflection. And then what you do at runtime is find the policy that best matches it. And the effect is a lot of complexity, and maybe unnecessary complexity. So again, it's a trade-off. Then finally, you have component-based design. Again, something that works in many cases and doesn't work in at least equally as many cases. What you do is you consider your big system as consisting of a bunch of replaceable components. Okay? And then the whole idea is that if something gets broken or that something needs to be optimized for specific environments, you just replace that component with another one. And the core issue here is, of course, that the interfaces remain exactly the same. Now, where does this work well? Well, to give you one example, it's the Apache web server. That thing is highly configurable, and I would argue that thing fits the bill when it comes to component-based design. Unfortunately, in many of these software organizations, there are many more dependencies than that is visible at the interface. There are all kinds of indirect dependencies between components, so that means that as soon as you pull out one component, you're actually pulling out a lot more of components, and your system will actually break. Nevertheless, people build software like this, and you could say that it's adaptive software. But my claim is that you may not need adaptive software, but you need adaptive systems. And that's actually something else. Okay, your software is not adaptive. Your software is a piece of code that you wrote, and once you wrote it, you can't change it. Well, you can still change it, but you don't want to change this on the fly. And I think what people mostly need are adaptive systems. And that's all about distributed systems. And if you start thinking about adaptivity in distributed systems, you will bump into self-managing distributed systems. There was a lot of hype about this, so let me just show you this one as well. There's a lot of hype going on there. It's called autonomous systems. And I'm not going to tell you how many papers have been written on autonomous systems, and these papers have no content whatsoever. Okay? And there's really no content. It's just blah, 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 blah. That doesn't matter, because there are lots of other papers that actually do have content on self-managing systems. And what I'll be doing today, I'll tell that in just a minute. I will give an example of a self-replicating system. Adaptivity comes in the form of self-configuration, self-management, self-healing, self-optimization, and a couple of years back, colleagues of mine, and including myself, we came up, well, let's just use a wild card, self-star. And actually, you can actually look up self-star systems. And these are systems, well, you fill in the star, we'll make it self, and hey, everybody's happy. Let's make this concrete. And actually, this is, I think, a very important slide. This is a very normal situation in systems. It talks about a core distributed system, and most of the course is actually about this part. But what we do in practice when we build real distributed systems, and a real distributed system is like the internet. Once it's up and running, you can't bring it down. Okay, you're not supposed to do that. So this thing just lives and lives and lives and lives, and hey, now you got yourself a problem, because how do you maintain these things? So you shut down parts of it, okay, or replace parts of it. But what you really do is the following. You have your core of your distributed system, and you measure output. And don't worry, I'm going to come to a very concrete example in just a minute. Once you have observed output, you try to measure what is going on. So you have a metric estimation part. Okay? Once you have your measured output, now comes the fun part. You do analysis. You do an analysis of what you just saw. And given the fact that you know what a good behavior would be, that's your reference input over here, you can take all kinds of measures to change the behavior of your distributed system. Okay? What I just described here is a so-called feedback control loop. And interestingly enough, what many of us do, including you, is either implicitly or explicitly build in these feedback control loops into our programs. And once you're doing that, what you're really doing is making a self-adaptive system. Because what you're doing is saying, listen, I can't predict exactly under which circumstances my program should be running, but once I have a good idea of what's going on in its environment, and that is basically this thing, these uncontrollable parameters. Okay, I don't know why this thing is letting me down. It's disturbance, it's noise. Then I can react to that, and I can adjust the behavior of the distributed system by doing things. And doing things could be, I'm going to place more replicas. I'm going to change my strategy when it comes to going to that server instead of that server. Those are all on-the-fly adaptations to make sure that your core distributed system behaves the way that you intended it to behave. Okay, what time are we doing? I'm going to give you an example. This is an old example. It's called Globule. We built this system a couple of years ago. We're done and over with this system. We stopped working on it 2, 3, 4 years ago, and then we continued on to other things. Most of the credits, by the way, go to Guillaume Pierre. This was this other guy who's now a professor in Rennes, who will now give me a chance to be one of the better teachers again. But he and I were working on this thing, but the basic idea comes from him. And the whole idea is that you basically build a collaborative content delivery network. Now, I briefly discussed what a content delivery network was. It's very simple. The easiest way to think of this is as follows. I have a website, and what the website does is try to push this content over to edge servers, okay? And what it's really concerned about is which content should I place where. And the whole idea is that there's a price to pay when you move content to edge servers. And edge servers could be caches, could be active replica servers, whatnot. It's stuff that is other than just the origin server, your web server, okay? And like I said, there's a cost, and we already discussed a number of these costs. There will always be a cost of latency, and there will be a bandwidth cost. But there may also be monetary costs. Like, hey, if I have a server over there and I have a network connection to that server, I may need to pay for the amount of data that I send over that connection. And you can easily come up with additional resources that will tell you how much you need to pay in order to get content from here at your site to one of these edge servers. Okay? Everybody has that model? Because that's important. So what you do is you take decisions driven by a general cost model. Now, the interesting thing is, if you take a look at what is over here, we're talking about resources with a weight. The weight expresses how important you find let's say, optimization on bandwidth, or how important you find optimization on latency, or how important you find to reduce your monetary costs. Or, for example, to give you another resource, if you move copies to edge servers, you are taking a risk with inconsistencies, right? You can express that, oh my God, I do or do not want to have inconsistent copies. And what you're doing here in this simple function is you're just adding these costs for the use of these resources, or the cost of inconsistencies. And you're just making one big basket of fruit. Apples and oranges that cannot be compared to each other. And when you see this for the first time, people say, what are you doing? You can't do that. How can you say anything sensible about one apple and one orange and you add them together? Well, the best thing you could say is you have two pieces of fruit. But that's not interesting. That cost over here has no dimension. It's not a monetary cost. It's a kind of a utility. It's a number. And the only thing that you're striving for is to minimize that number. Okay? So if your goal is to minimize the number of pieces of fruit that you have, and you're now talking about apples, oranges, and grapes, you can say, I prefer to have lots of grapes, but not too many apples. But the total amount of fruit pieces that I have should not exceed a certain level. And now I'm even still comparing in terms of fruit, okay? But it should be just a number. Okay. How does this work in practice? So this is basically the scheme I just discussed. You have your origin server over here. You have a bunch of edge servers over here, okay? And the whole idea is just move content to those edge servers. And the only thing you need to do is to take a decision which content and under which conditions. That's it. Okay. Now, what did we do in Globule? We did what-if analysis. What we said is, okay, suppose I had replicated that web page over to that server. What would I have gained? And it's not a matter of expressing the gain in how much would I have improved the client's performance. That's not important. It's just one of those cost factors. And the only thing that we were doing is trying to minimize the total cost. Okay? And every time you take a decision on moving something to somewhere else or not, you are basically following strategy, a replication strategy. And what we wanted to do is always select the best replication strategy for the entire site. That was the whole idea. Okay. So we did an experiment. And just to make it clear, you're going to see some numbers in just a minute. And look, this is old, okay? We're talking about stuff we did about 10 years ago. This was based on data that was 12 years ago old. That doesn't really matter. Okay. This is the picture that you have to bear in mind. Okay, what I wanted to say just a moment, I am now violating the rule that I said on Tuesday. I will not talk about stuff that is not in the book. I am talking about stuff in the book, which means, that is not in the book, which means that you don't need to know this by heart. I'm giving this as an illustration, very concrete, on a self-replicating system. And once I've done that, I hope that you will understand, oh, this is not just hype stuff, there's actually content with self-star. Okay, that's the reason why I'm telling you this. And it's fun stuff because, it's research, okay? So what we did is assume the following. You have an origin server over here, and the interesting thing is all requests always initially come to the origin server. So I know what is always being asked, right? Knowing that, you can build up models. You know where your edge servers are, okay? They're over there. But these things are for real. They're really in autonomous systems. They're out there at ISPs. Your requests under normal conditions can actually be traced back to where they came from, the original ISP. So what I could do is to say, listen, I just got a request, let's say from this client over there, and I know, whoops, oh, this is terrible. Let me do it like this. I got a request from this client over there, and that initially, that request came directly to the origin server, but what would have happened if that client could have directly gotten the content from its associated edge server? Okay, that's what we're doing in the what-if analysis. Suppose I had put the content that that client was requesting for at that edge server. And we do this for all requests, and there are always a couple of requests that you don't know where they came from. So we say, okay, they just went directly to the origin server, and of course I have my own whoops, what did I do? No? I pushed a button that I wasn't supposed to push. Okay, sorry about that. But you get the idea? The origin server knows where all the requests comes from and then can play a game. What if I had served that request from an edge server? So what we then did is, basically I just mentioned this, we collected a bunch of traces and requests and, very important, also the updates. And just think how you can record updates without modifying an operating system. It's not easy. Okay, you have to apply tricks. But hey, that's systems work. That's nice. And we collected stuff from 2 servers in Amsterdam and Erlangen. Okay, and for every request we checked where it came from, average delay to that client. You can just ping, you can get reasonable information about that. And we actually computed the average bandwidth. And these are good examples where you can say, oh yeah, sure, yeah, that's sure, yeah, easy, right? No, not entirely. Okay? And I'll just let you guys think of how you could actually measure the average bandwidth to a client. And you'll be surprised that it's not that easy. Okay? You can't just start pumping a lot of data, for one. Then we removed some noise, the page that were requested less than 10 times, and then we started replaying trace files. So now you have to imagine, this is a situation. We have an origin server, it knows where edge servers are, we have traces, okay, and then we simulate in real time taking a trace file on, hey, what would have happened if we had served that request from that edge server over there? Is this picture clear to everyone? If not, just let me know. Yes?
You said that, can you say again, because I'm not...
Okay, so this is the overall model. I am a web server, a real server, just a machine. I get requests. I record all the requests. That's called a trace. Okay, so I know exactly what's coming in, what's being requested from me. Okay, so that's one thing. I pretend that I have servers all over the internet. Okay? I know the latency between me and those servers. I know the bandwidth between me and those. No, I know what clients are asking for when it comes to bandwidth, and I know what I can serve bandwidth-wise. I'm assuming that all that information is there. These are realistic assumptions, by the way. Okay? And then I do the following. I get these requests, and I ask myself, okay, for, let's say, Maarten's homepage, what would have happened with this trace file if I had replicated that page on that server, and that server? Would I have saved on bandwidth? Would I have improved on latency? And would I have reduced my monetary costs? Okay? And the interesting thing is, I'm doing this in real time. So I'm here a server, I have a compute server over here. Then I'm saying, okay, compute server, here's the trace file, do your work. I'll give you a few numbers in just a minute. Okay? And this thing is just pumping data, burning CPU cycles to give me back an answer like, you just had the wrong strategy for Maarten's page. Okay? Here's some data. The interesting thing is that we just get lots of requests. Okay? And if you take a look at how many autonomous systems we actually hit, well, it's actually not very impressive. It's site 1, that was us, I think. Yes. So that was the VU, this was Erlangen. Just a few thousand. Well, yesterday or the day before, I told you that there are approximately 30,000 autonomous systems. Okay? But yeah, most requests actually come from very few autonomous systems because there are only a few important ones. Okay? And I think that's actually on another slide. What is it? 70% of all the requests come only from a handful of autonomous systems. This holds for virtually all websites. Okay? Now, let's focus on strategies. What can you do? Well, there are caching strategies. One thing you can do is not replicate a page. Don't replicate Martin's homepage. It's really not worth the trouble at all. So that's one strategy. Another strategy could be, hey, what I can do is I can tell edge servers to cache documents. So once a client has requested it, the page is moved to a cache, okay? And then the next time the client would ask for that same page, it checks whether that, for example, that page is still up to date. That's called a CV, verification. You could also, this is actually what was proposed in the original HTTP protocol. You can also have the limited validity. Basically, is edge servers cache documents and they don't go to the server for a certain time. Or delayed verification is another one. And it really doesn't matter. There are different strategies. Likewise, you can have a kind of things that the server can do is say, okay, listen, I know the data is out there at the edge server. I will just send a notification as soon as I get an update saying, hey, your stuff, what you have over there is no longer valid. That's the only thing you do. Later, the server will come back to you to get a fresh copy, but this is the only message you send. Other strategy could be, listen, the page has just been updated. Here it is. Okay, so you push content to the server. And then there are a couple of hybrid strategies. For now, it's not important to understand these different strategies, but just that you realize that, oh yes, there are different strategies. So now I can make decisions on which strategy would be the best. So what this thing shows you, this table shows you, is the following. What normally happens is that you have a global replication strategy for an entire site. All documents adhere to the same replication strategy. And based on the traces that we had, what this table tells you is that if you would count the total turnaround time for a client, okay? You send a request, when do you get the page back? Or you simply start counting the number of stale documents that are returned. So typically, if you would cache a document and not verify whether it had been updated, you are taking the risk that you're actually being returned something that is old. Okay? So that's another cost that you can take into account. Or the total bandwidth that you're pumping through the internet by moving pages between a server and an edge server. If you follow any of these strategies and apply that strategy blindly to all documents, what you'll notice is that some strategies will optimize on the number of returned stale documents, but then again, they will not be best when it comes to using bandwidth, okay? Or they will not be best when it comes to the total turnaround time. On the other hand, if you want the best on the total turnaround time, you actually may be returning stale documents. Okay? So the conclusion here is there is no single strategy that works best for all documents. Okay? So what we did was we applied a per page strategy. And what this thing tells you is actually quite interesting. These points over, whoops, where is it? Sorry about that. The points here show what would happen if you would apply a strategy to all pages, okay? And these are so-called cost function arrangements. What I'm doing is the following. I told you about the weights. I said, okay, you may want to be interested in latency or bandwidth, and you can't really compare latency and bandwidth. So what I can do is, listen, I know what the optimal strategy could be. That's actually the so-called ideal arrangement. If I would just take a look at every individual document, this is the best that I could get. To make it concrete, we didn't want to have any stale documents. We were just looking at other graph doesn't really matter. I have to have this one. The total turnaround time. What was the best total turnaround time that I had? It was 100 in this other table, okay? And what was the best total consumed bandwidth? It was, I don't know, it was probably something like 100. Okay, 100, okay, 100, I normalized everything, by the way. So, no matter what, the best that I can do is combine all these best figures. Okay? Now, what this thing tells you is that regardless the combination of weights you choose. Okay, so regardless whether you consider latency better than bandwidth, it shows that all these optimal values, irrespective of the weights you choose on the importance for a metric, will always give you a point somewhere on this curve. Am I making myself clear? And what it tells you is that any point on this curve is better than any point out here. So what I just told you is that no matter what, if you would have a per page replication strategy, that's the best thing you can do, regardless whether you find latency more important than bandwidth. It really doesn't matter what your choice of preference is, you'll always be better off than taking a single global strategy for your entire site. Okay. The interesting thing is, let's take a look at which strategies were actually used. And the most interesting observation is that this one over here, CDV, which is cached with delayed verification, which is a default web caching strategy, was not used by any page at all. And what it just tells you, oh, nice, such a policy of caching documents. Unfortunately, it's of use to no one. Okay? And basically, it also shows you that for most strategies, they were chosen for pages. Okay? These are all fractions of when they were chosen. Meaning, this is the bad news, meaning that you got to have a lot of strategies to actually optimize things. Okay? So you need a self-adapting system, a self-replicating system. Okay. And I think that was the last one. Yes. Before we take a break, I have only one question for you. These results were based on real-time simulations of trace files and doing a what-if analysis. Okay, how big should a trace file be? And now think in terms of extremes. And we're really talking about web traces. If I would have a trace file consisting of only 2 requests, would that be enough? Would not be good. You just don't have enough information. Okay? What about taking a trace file with thousands of requests? You know, spanning, let's say, 10 days. Would that be a good idea? Why not?
It is because the changes are so dynamic, you can't for such a long period.
Exactly. The reason, no, I have to say one thing. This whole system is based on a very simple assumption. Recent past will be the same in the near future. Okay? So what I measure in the past is probably what I can best expect for the future. Okay? If you take a very long past, you're missing exactly all the dynamics in that past. You're flattening everything out. So if you do that, you'll actually get a very poor prediction for the near future. But if you take a very small past, then hey, that's not good for predicting the future. So there's somewhere an optimum of how many requests you should take to actually make a very good prediction for the future, right? We fixed it to 500 requests. Turned out nicely. Well, actually, we were off by approximately 3% or something like that. And if I would draw, and I can't show this on the screen then, draw the graph and say, hey, okay, this is the length of the trace file, and this is the percentage of error that I found in my prediction, the graph would look something like this. Okay, I'm exaggerating a bit. So it's really bad for very small traces. It's really not good for very long traces. It's somewhere in the middle. It's over here. And now, of course, you understand what you could do. You could make a feedback control loop to discover what the trace file should be now. We didn't do that, but there's another feedback control loop you can take into account instead of fixing this to 500 requests. Maybe it varies between 450 and 550. Okay? We're we're doing real-time simulations. How long do you think it will take to simulate a full suite of replication strategies for a single web page? What will be a reasonable number? Let's see if you guys have any clue on computations. Give me a number. And we're talking about 10 years ago. 1 day. Wouldn't be good for our system, by the way, but okay, 1 day. Give me another number. Couple of hours. Oh, I like this.
10 hours.
10 hours, okay. 140 milliseconds. So test your sense of computability, okay? 140 milliseconds. And you know what? With a few tricks, you can bring this down to 14 milliseconds. And the trick, for example, is, what did I predict last time? It's probably just as good. So let me first evaluate that strategy and chop off the other ones. You can have a tenfold improvement. Which means that it actually makes sense, this is on a per-page basis, right? It makes sense to have real-time, what-if simulations using traces to evaluate what you should do next. Because within 14 milliseconds, you know exactly what to do for that page. That's systems work. Okay? But if I would have a gut feeling that it would take a whole day, I wouldn't even start this research. Okay?